So question number 1, for a particle in a 3D box of a cubic, the energy is given by the following equation, in which you have 3 quantum numbers, nx, ny, and z. They are all integers. What is lowest energy? Obviously, lowest energy when nx, ny, and z are all lowest, which is 1. Okay, so these are 1, 1, 1. And that gives you 3h squared divided by 8ma squared. This is a non-zero point energy. Okay, what is the degeneracy of the level that has energy twice of this one, of this lowest energy? So twice will be 6h squared divided by 8ma squared. Now, the allowed energy can only be this equation. So if this is one of them, and that means the combination of nx, ny, and z should be 6. So what's the possibility? 1, 1, 2, 2, 1, 1, 1, 2, 1. These are 3 possible combinations of nx, ny, and z. And they give you 3 different states, but has the same energy, because when they combine together, that give you 6, give you the same energy. Now you have seen this question again in lecture notes, in homework, all right? But important thing is the degeneracy not always 3. It can be other values. For example, what if the given energy level is, let's say, 12 h squared divided by 8ma squared? All right. So again, this belongs to the allowed energy level. That means nx squared plus ny squared plus nz squared equals 12. So what's the possibility? Nx, ny, and this can only give you one possibility. That's 2, 2, 2. All right, 2 squared, 2 squared, 2, that gives you 12. And this is the only possibility. So that means the degeneracy is 1. Is 1, because you only have one state. Well, nx, ny, and z are all 2. The energy equation is 12 h squared divided by 8ma squared. Okay. Question number 2. For a particle in a square box of side L, at which position is the probability density and maximum if the wave function has n equals 2, n equals 2, and 1 equals 2, and 2 also equals 2? For a square 2D box, the wave function equation is like this one. It's determined by 2 quantum numbers, nx and y. Okay, so remember, for 3-dimensional you have 3 quantum numbers. For 2-dimensional you have 2 of them. And here is 4 divided by ab, and if it's a square, then a equals b. Both are L, so it's L squared. So square root 4 over L squared give you 2 over L, sine 2 pi x L, sine 2 pi r y L, when both quantum numbers are 2. Okay, both are 2. So that gives you the wave function like this. All right, so the question is, where is the maximum probability? For probability, you need to square the wave function. Okay, the maximum is when these 2 are maximum, and we know that the sine maximum is 1. So remember, this is, let me draw the sine. Okay, so sine looks like this. So this is 0, this is pi, this is pi, this is 2 pi, this is a half pi, this is 3 over 2 pi, and this is 1, and this is negative 1. Okay, so you see the maximum is 1, the minimum is negative 1, but if you square it, both becomes 1. Okay, so the maximum is when both squared equals 1. And for this one, it can be positive 1, negative 1. So for positive 1, it's half pi. That's this one. For negative 1, it's 3 over 2 pi. Okay, so solving it, the x is L over 4, 3L over 4. That's the x location, where you have maximum, give you x assigned to be 1 or -1. When they square, give you maximum. Similarly, for y, you do the same. Okay, and that give you L equals 4, 3L equals over 4. So where is the location for 2D box? You should combine x and y. So you have 4 possibilities. This combined with this, all right, and that give you the 4 possibilities. So this is due to x, all right, and this is due to this with this y. Okay, and then this can combine with this one, this combine with this one. So you have 4 possibilities. So how does it look like? This is the wave function probability of the wave function. How does it look like? So let's say this is x, and this is y. All right, L here, L here. So the maximum, the first maximum is when x equals L over 4. And y is also L over 4, right? And this one, maximum, here is 3 over 4L, and this is half over 4. So y is half L 4. Okay, so that's this one. And what about this one? Both xy is 3 over 4L, 3 over 4L. All right, so 4 maximums. Now, where is the nodes? Okay, nodes. Nodes is when the wave function goes to 0. So if you look at this wave function equation, all right, for this to be 0, then sine 2 pi x should be 0, or sine 2 pi L y should be 0. And again, let's look at this one. When can this be 0? It can be pi. Pi is 0, or 2 pi, and therefore, well, our solution is sine 2 pi x over L is 0, and so this can be, let's say this is pi. This is pi, so that sine 2 pi x over L is 0. That's a node. And how can this be pi? We'll solve it. X will be L over 2. So x L equals over 2 is the solution of this one. Okay, or y L over 2, that give you this 0. So how does this look like in this plot? Well, it's this line. You see this line? All the points in this line, the wave function is 0. Or this line. You see this line? This is when L over 2, when y is L over 2. Here, this one is when x is L over 2 for this line. Okay, so these lines, wave function are all 0. These are nodes, 2 lines. Describe the physical origin of the quantum mechanical tunneling. Quantum mechanical tunneling is about particles penetrate into classical forbidden region. And this is because in quantum mechanics, the wave function is particles is described by wave function, and the probability is square of the wave function. So if the wave function is not 0, then you have a probability to be there. Okay, so here we say that the quantum mechanical tunneling is related to the probability density of the particle, which is square of the wave function. So if you have an energy barrier, all right, you have a high energy, then the wave function start to decay exponentially, as we see. So let's say you have a wave function, but then you have, this is energy barrier, so it start to decay. Okay, it's not a good drawing. And so it decay. But if this barrier is not too thick, then at the other side is not 0 yet. Okay, it will go to 0, but it's not 0 if it's not too thick. So then if this side is free particle, so then just like this side, it start to oscillate, but with a smaller amplitude, and because this is not non-zero at the other side. And so if the wave function is non-zero, that implies the particle has tunneled through the barrier. Okay. So next, explain why tunneling is more likely for the particle with 3/4 V0. V0 is a potential energy, then 1/4 V0. Okay. In other words, why particle with higher energy is more likely to tunnel than the lower energy wave function. Okay. So here is a drawing, and let me erase that one. Okay, and you can see here the low energy wave function here. This low energy wave function decays much faster than the higher energy. So the other side wave function has a much larger value than the wave function with low energy. Okay, so tunneling more likely to tunnel. But why? Well, we'll look at the equation for the wave function. So this is the wave function decay inside the barrier. Okay, so at the other side, the wave function x is a, is the length a. Okay, and so you should have a e negative ka. That's the wave function at the right side. And therefore, the probability, you square it. That's the probability at the right side. Okay, and that's why you have this equation. Okay, and from this equation, you can see here, the A is the length. The smaller the barrier, the larger the probability. You have a mass here. The smaller the mass, the larger the probability. So electrons is more important than photons, than neutron, than protons, than molecules, because small, larger probability to tunnel. Okay, and you also have energy here. All right, here the larger this energy, the larger the probability. Okay, so tunneling, transmission tunneling probability decrease exponentially with the thickness according to the equation, square root of the energy difference between system and the barrier, and the square root of mass of the particle.